Today I'm going to be talking about sort of the Internet of Things approach as well as comparing into it messaging constructs, data movement environments, and some of the problems and considerations. I'm going to talk about the standards efforts that have evolved around this, do a little bit of compare and contrast to the various standards efforts here, talk about the message exchange patterns, all those various things. First, I'm Dave McAllister. I am the Director for Developer Engineering for Solace. Solace has been in the messaging business since 2004. We run about 90% of international banks' transactions. We run 70% of all the world's currency exchanges. We power Union Pacific's entire IoT environments. We are the backbone for Singapore's smart city with all of those efforts. I'll show you a couple of things and we'll talk about some of the actual implementations and cases specific to those environments as well as we move forward. Probably a little bit about me. I am an official geek. I won a Golden Penguin in 2002. I started with Linux in 1994. I have open source roots that go pretty deep. And even though I am not a lawyer, I can out-argue most lawyers when it comes to open source licensing codes. So much so that I occasionally get accused of having a law degree, which I do not have. Fair disclaimer, I actually read user license agreements. So I'm probably the only person in the room that can actually make that single statement here. So when we talk about this, elements of IoT, we're going to cover a handful of different things here. We're going to talk about some of the top level considerations, what you need to think about when you're considering and looking at building an IoT solution. We're going to look at some of the different architectures and the architecture changes that are necessary when you consider IoT here. And finally, we're going to cover the standards and where it makes sense to use the standards and where it doesn't make sense to use the standards. Fair caveat. I, in particular, and my company believe that there is no absolutely one right answer. The right answer is the one that fits you. There are lots of standards. The standards have different uses and different cases that they make sense in. We think you should be able to use the ones that you need to use when you need to use them. So when we think about systems here, the systems really come down to a number of characteristics. These are characteristics that in general you think about for any architectural approach here. You think about the scale of devices. This is probably where Internet of Things has the biggest set of difficulties. Let's pick on Daimler, for instance. Daimler wants to connect 20 million cars passing a minimum of 4 messages per second to this. So think about it, 20 million cars, 4 messages per second. Those messages include things like speed, condition, location, all those various pieces of information. It's 800,000 messages per second going on. So the scale can really creep up on you when you start talking about IoT. This is a big issue because everybody likes to start small and then grow. With IoT, you need to scale when you start. The capability of devices. Not all devices at the IoT space are the same. For instance, Texas Instruments makes this wonderful little sensor kit. If you ever want to play, there's a little thing just called sensor kit, Texas Instruments sensor kit. It's about that big. It's self-contained. The batteries last for about 2 years. And it will tell you the temperature, the location, the acceleration, the direction that you're moving in, whether it's light or dark, all those things inside of that. So it's actually a fairly capable system. It's one way. Directional goes out, it doesn't come back. So that's the other thing that can trap it into you, capability of devices. Are you talking one direction? Or are you talking both directions inside of here? Message exchange patterns, and we'll spend a little bit more time talking about message exchange patterns. But basically, what is the message trying to accomplish and how you choose to accomplish it? Everybody's heard of pub/sub, right? Hopefully. If you're in here, you've probably heard of publish, subscribe inside of here. But there are lots of other characteristical message exchange patterns that creep into here. And then finally, QoS. Do you care whether the message gets through? Or do you really just want the next message that shows up, whatever time it shows up inside of here? Traffic characteristics. How bursty is it? How saturated is it? Again, most people have heard that Amazon around the holiday time frame has to turn on additional data centers. It's a slow burst, but it's a bursty traffic. I'd be willing to bet you that the Securities and Exchange websites had a real headache of a time last night. And I happen to know my company is based in Canada, that the Canadian National Site for Immigration crashed last night, very honestly, right here. If you're not worried about security, worry about security. We recently had the DDoS hit that was tied to a series of video cameras, IoT devices. There's a new one out here that talks to Philips Hue. If you've seen the light bulbs that you change colors and so forth. There's now a little virus that's been developed that flies on a little drone, and as your drone gets closer to the Philips Hue lights, it infects them. And it can fly past you. And the demonstrations are quite cool because what they do is they fly the drone past the building and the Philips Hue lights start blinking SOS. That's their demonstration technique. So worry about security inside of here. And then finally, you got this wonderful IoT thing. What the heck are you going to do with it? You probably have a data center or a cloud someplace that all fits into it. So these are all just system requirements that fall into that. But here's the problem statement. You got this really cool set of devices down here on the bottom. They can be, manufacturing, can be smart house, cameras, trains, vehicles, all sorts of things. And then up here on the top, you have some sort of data center thing, data storage, somebody looking at it for analytics, a server environment, storing off data. Very simple, very clean. Well, let's make it a little simpler here. Let's make everything down at the bottom the same device, so you don't have to worry about differences in devices right here. And you build this out, and you connect them all in, and all you're going to do is data ingest. You're just going to take all the data from here, and you're going to stick it into the data pool, okay? What is the one thing you can guarantee that's going to happen right off the bat? You're going to add more devices. Your scale is going to grow at the bottom. And as your scale grows at the bottom, your scale is going to grow at the top at the same point in time. Now you've got to worry about things like load balancing that fall into place here. And then you probably have to worry a little bit about security. So you probably set up sort of the demilitarized zone that goes between your devices out here and your data center out here. And then you got all your other applications that want to do something with this data. And then they have to talk to each other as well and talk to the data pool. Okay, pretty straightforward. You have no idea how many devices you're going to have down at the bottom here. You have no idea what your scale is going to be at the top, very honestly. And just to make life more complicated, you can pretty much guarantee at some point in time those devices are going to get upgraded. They're probably going to have more capabilities, and you're probably going to want to talk back to them. So all of a sudden, you've got two levels of traffic that are going on here, and then you can have all these other devices all at the same time. So the problem is not so much of saying, I want to have these 5 devices talking to me and dumping data in. The problem is actually an architectural problem that says, I have some number of devices down here. I have devices that I haven't even thought of yet here, and I want to talk both ways, and something up here needs to consume all of those different pieces. This is a problem that, if you go way back in the dark ages, like where I was solved with originally with networking. We had networks all connected together. Then we had network routers. Routers now deliver the messages to where they need to go. Message routers, message buses do the same type of concept. So connecting 2 computers together, WebSockets is pretty easy. It's one line, one connection, not too bad. That's here. If you connect 3, you have 3 connections. Anybody want to take a wild guess at 4? Very simple math equation for here. 4 is 6 connections. Number of machines times the number of machines minus 1 divided by 2 is the number of connections to connect all of the devices together. Okay, so you got 10 devices. You're now hand coding 45 connections. You have 100 devices. You're now hand coding 4,950 connections. And by the way, I have never done the math for Singapore Smart Cities cars, which is 200,000. I've never done the math of the number of connections you'd have to do that. That's because it's easier just to set up something in the middle that acts sort of like a router that handles all the messages for you, and every device connects to it once. So messaging has the same concept. There are headers, and the headers get looked at and determine where things go. So standard IoT interlude here. If you haven't seen this, XKCD, it's very telling. And this is one of the nightmares. This is where you can actually tap in and see this. But, you know, I will guarantee if I ever get a self-driving car, after seeing this cartoon, I will not leave it running because I don't want my car to end up in Anchorage, Alaska. So, how do we deploy these things? And now we're going to get a little bit into sort of an architectural view of the world here. We have a number of devices down here at the bottom. And this is usually called the fog layer. Fog layer, close to the ground. It's kind of fuzzy. We don't really know what it's doing or what it looks like inside of here. And these devices can be capable of one direction, bi-direction, but they all need to talk some way, whether it's TCP, UDP, Bluetooth low energy, or something that, you know, Zigbee. It doesn't matter at this point in time. But those are the things. They talk to what's usually called an edge layer. And the edge layer does the first level of load balancing. That load balancer can be considered a connection tier. And this connection tier, rather than talking completely to the next layer, is set up to provide you the capability, again, of isolating the various pieces. So your fog layer talks into your connection tier. Your connection tier does its set of balancing, and then it talks to the enterprise bus. Almost everybody has some level of enterprise bus at some point in time here. These are common names. There's a core environment, there's an edge environment, and there's a fog environment. Sometimes you'll see the fog environment get argued about. In here I call it a fog environment because I love the concept of not actually knowing what's going on inside of here. Each of these pieces have to be able to talk both ways. This architecture is very standard. You'll see in the IoT space. A three-tiered architecture isolating each of the functionality so that when you scale, you only scale the necessary component set. Rather than trying to scale two ends at once, you only scale the pieces that you need to scale. So again, system considerations. Let's make it a little more realistic. Both your connection tier and your enterprise bus are not just one little magical thing that fits inside of here. They're probably a bunch of different devices. Those devices themselves all have to talk, and that's why you have a load balancer that fits inside of this picture here. And they then communicate through some method as well here. But again, there's a scaling issue that falls into here. This is made up by what you talk to connections. How many places do you touch between here, 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 and there, which are usually in messaging space called queues. And then how do you do subscription basis? So again, this laptop up here wants to know what the temperature in the house is. You know, this is the Nest problem. So you want to know what your temperature is. You want to be able to put out. How does he talk to here? He's got multiple layers that he goes through. And we'll talk about that a little bit more in detail as we go through here. But in general, there's this thing called subscriptions. Subscriptions, pub-sub, publish-subscribe model, basically says somewhere down here, this guy is publishing data into this cloud, and this guy is interested in that data. To use an example here, just talking with one of my colleagues, we have a geofence environment. So geofence says, I got a whole bunch of taxi cabs running around Midtown, New York. I want to know when they leave the island. So I geofence that. Or I want to know when they are not at Times Square, and I geofence that environment. And he got the bright idea of saying, I want to know when my son is not in school, very honestly. I can pretty much guarantee most of the other parents don't care where his son is, but he does. So he subscribes to the message that says, where is my son? And by the way, he's really only interested in two things. Did my son get to school on time? So it's a time consideration filter. And did my son leave school before time? The second one, he wants all of those events. The first one, he just wants the one event. So there becomes those two characteristics of how you subscribe. In IoT, you will hear the word subscriptions referred to slightly differently. You'll hear them referred to as topics, and that's because of MQTT. I said we'd talk a little bit about message exchange patterns. There are pretty much 4 that fall into the IoT space here. First one, obvious, device-initiated publish subscribe. This is where the device down here publishes a piece of information, whoops, wrong button, publishes a piece of information, and somebody up here wants to know about it. Very honestly, you'll see a lot of subscribes into your data pool. Everybody wants to record all the possible data until you don't want to record it. You may only be interested in one piece of information, which is the latest piece of information, not all of the data that lives inside of here. The second one is what's called device-initiated request reply. That's a device down here that says, I want to talk to my application up here and ask for something specific. What do I do next? Where's my update? All those different things. The first one is what's called a common message pattern. Everybody wants to take part in the publish-subscribe model. The second one is a personal connection. I am the only one that's interested in those pieces. And then you can do the same thing, but starting from the other direction. This guy talks to down here and says, here is your subscription. Here is your update for here. Or he can say, okay, all of you guys down here, I got an update waiting for you. When you're not busy, come get it. And that's the last one, initiated request reply. In IoT space, there are 2 common ones, device-initiated pub/sub and cloud-initiated request reply. Cloud, by the way, I'm using as a generic term, data center, private cloud, public cloud, hybrid cloud. It's where your basic application space lives versus where your devices live here. And then we get into quality of service, QoS. There are lots of different levels of QoS, but in IoT space, there's really kind of 2 that most people consider. And I can spend the next hour talking about QoSs as well. But really, I'm going to use the MQTT model here. MQTT QoS 0, which says at most once. MQTT 1, or QoS 1, which says at least once. So at most once, I'm going to send it out there. Somebody gets it, great. The next one says, I'm going to send it out there and I'm going to keep it there until somebody replies back and says, I got it. There's a 2 which says exactly once, QoS 2, which says, I wanted to make sure that it got there and I only want one person to respond to it. So the first one who gets it and replies is the person, and after that, it's gone. So those are the 2. But usually you see in IoT space, 0 and 1. The final one is a little bit more tricky, and I'll drill into this one a little bit more as well, which is how does this guy talk to this device through 2 different sets of buses? Yeah, that's an interesting challenge. So he comes in, he's load balanced to this connection tier or to this connection tier. You don't know, very honestly. This guy up here is talking to this guy, but he's talking to another entirely separate thing. He doesn't know. He knows the device lives out there. He knows he got a message. How does he get the message back? And then you put this into scale of 20 million possible queues, something along those lines. This becomes a challenge. So how does this guy manage to make sure that he gets it to here, manage to make it here? I will tell you right now, all of the solutions are miserable, but they exist. And it uses queues to topics to reverse engineer these things. It's non-trivial. There's no good solutions. In the standards bodies, MQTT and AMQP are trying to solve these pieces, but it's non-trivial. The scale is daunting that we do this. But that's called the single point of contact. As an app, I just want to talk to one place. As a device, I just want to talk to one place. Don't give me all these 10,000 possible message routers and queues and so forth. So that really becomes this issue. How do I tell it that I got the message for here? How does it find it? It can be millions of these things. How does it find which one it needs to talk to here? And then when the app is talking to it, how does it find it in the first place and make sure it's talking to the right device? So these are both, if you think about it, QoS 1 problems. QoS 0 problem, ship it out there and hope that it gets to the right place. QoS one problem says it's got to stay alive until you know it's been received. So QoS makes a major headache inside of here, but it is probably the most important thing. Imagine that you've got a shipping container and you're shipping, I'm going to pick on orchids coming across from Asia. They do this all the time coming into San Francisco. For some reason, the orchids love to bloom in San Francisco fog. I've not quite understood this, but nonetheless. If that shipping container gets too warm, you end up with a whole bunch of dead orchids. If the shipping container gets too cold, you end up with a whole bunch of dead orchids. And so they constantly monitor the temperature for this. If the temperature goes up too high right now, there's a guy that walks around and checks temperature on the outside of shipping containers, full of orchids for here. And in an IoT environment, that would all be going into more process control basis. You'd be seeing it on a nice screen, SCADA type of level, and then you say, go change the temperature, or you'd see it and it let it change the temperature automatically. Still, that's a big problem. There's a lot of containers that ship on those ships. So, a little bit on this. This is sort of a high-level viewpoint. We're going to talk about each of these things a little bit more. There are obviously proprietary solutions. Messaging is not new. It started in 92, 93 with IBM MQ. TIBCO came along with EMS. They're both proprietary. Now, at the same point in time, this new thing came out 15 years ago called JMS, Java Messaging Service. And JMS is one of the mechanisms by which you can pass these things. Almost all enterprises using Java make use of JMS. So we'll come back to talk about JMS because JMS is actually incredibly important as a bridging construct here. HTTP and REST, everybody should know about, post and get. Here, what's the problem with HTTP and REST? Unidirectional. It only talks one way. Now, the good thing is that it's built into everything, very honestly, for that. AMQP is a standard. It was approved in 2014. It's an advanced messaging queue protocol. And it has companions to it for a couple of interesting things here. There's an open source project called Qpid. Qpid is in Apache Foundation, and it provides the API that implements the AMQP wire protocol. And then MQTT, which used to stand for message queuing, telemetry, blah, 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 which now stands for MQTT. For those of you who are in that weird category, you can also look at somebody and say, what does ECMA, ECMA stand for? It used to stand for the European Computer Manufacturers Association, and now it stands for ECMA. So MQTT is in the same category. It just is MQTT at this point in time. It is the biggest use for IoT. It is the major protocol. Came out of an expansion of the MQ. IBM Engineering came up with this. It came out of an expansion with MQ back in 1999. It's, I think, now version 7 of the standard, version 7, 7.1, something like that. And it has a companion open source project called PAHO, which is the API that implements it. The nice thing is that Qpid and PAHO support multiple languages. JMS, obviously Java only. The nice thing about Qpid is Qpid was built to solve a major problem with JMS. And I'll talk about that in the JMS slide here. And then down here at the bottom is this thing called CoAP, Connection Application Protocol. And CoAP is incredibly lightweight, incredibly small. It has a small problem, which I'll talk about in a minute, but there are dozens of open source protocols that work with it. So AMQP supports almost every messaging exchange protocol pattern known to mankind. It was built to solve a specific JMS problem, which is that it supports all the possible languages inside of here. It supports all those classes of service. 0, 1, 2, there's actually a 3 and a 4 coming for this. It has detailed message headers. So it can actually, in the message header, say specifically who gets to see this thing and what the security aspect looks like. And those messages can be encoded on the fly. So security aspects are built into AMQP here. It supports both TCP levels, so networking things, UDP levels, so a little bit different performance, but doesn't cross subnet boundaries. It is designed for enterprise computing, very honestly. Therefore, its power requirements, memory requirements, processing requirements are much higher than we can use at a device level for here. And its header fields are huge. Comparatively speaking, they're gigantic. And when we talk about devices and bandwidth, the size of the message fields becomes important. MQTT, lightweight, low power consumption. The little TI sensor that I talked about has a single battery in it. The battery lasts for a good solid 2 years running constantly without even blinking hard for this here. Message header can be 2 bytes, which is about as small as you can possibly get. Not a lot of information you can carry there, but it's still there. And it supports most of the major IoT. So QoS 0 and 1 are supported. 2 is mostly supported. That's the one that says only once, but it's mostly supported here. And there is a specific version called SN, which is for all the other connections. You want to run it across UDP, you want to run it across Zigbee, you want it across Bluetooth low energy, you want to run it across whatever protocol. There's probably something in SN that supports it. Now, on the bad side, there's no thing that says what this message's property is. So that doesn't actually let you know what the message is, it lets you know where the message is going. And because of that, you can't have header fields. So all I can say is, this is where I'm going. So there's no other information that gets encoded into here. And because of that, once it goes into a message queue, it's in the message queue, and MQTT doesn't care what happens to it after that. Other than that, it's probably the best choice. JMS, we talked a little bit. Everybody uses JMS. It's been around for 15 years. Oops, for that. Therefore, it's really easy to integrate. If you've got an AJMS support here, most JMS APIs are embedded in systems. They just come as part of the system here, and it supports all those classes of service as well. In device terms, JMS is pretty heavyweight. Again, takes a lot of power inside of here. And unfortunately, because JMS simply defines the API, the protocol, it doesn't define an API. Almost every single JMS stack is different. You have to have the same JMS stack on every single piece before the JMSs will talk. Believe it or not, that's what drove the formation of AMQP. JMS and AMQP, from a protocol basis, are pretty darn close here. But AMQP supports all the other languages, and AMQP supports a protocol exchange between all these possible stacks. The nice thing is, the first thing we built with AMQP was a JMS interface. So if you've got JMS, you can stick AMQP inside, and your JMS apps don't care. They just see JMS. REST, everybody's familiar with REST again. For here, lowest common denominator, post-git. There are no exchange protocols really here. Reliability is application dependent. You put something out there, the application is responsible for whether it gets it or not, or asks for it again. You have no guarantees of any sort on the quality of service thing. And then finally, CoAP, which we talked a little bit about. No TCP, only UDP, subnet only. Blindingly fast communication, incredibly low power requirements, but if you're going across the subnet, you got to have a bridge. And your bridge is non-trivial to set up here. And it is only right now request reply. So that makes it as one-to-one. Every single thing in CoAP is one-to-one. This device asks this device to get something back. Publish subscribe has been promised. It's coming. It's not here anytime soon. MQTT is the exact opposite problem. It's always many-to-many. You always have to set up queues and subscriptions, or MQT topics and subscriptions inside of here. They are both standards, OASIS and ISO for MQTT, IETF for CoAP here. And as I mentioned, MQTT has 3 levels of quality of service. CoAP only has 2 levels of quality of service. But for IoT, most people want 2. 3 doesn't make a lot of sense for that. So let's talk a little bit more about this. The fog, driven by device constraints, what the device can do, what you want it to do, how you want to get it there, and its traffic considerations that all fall into place here. What time is it? Okay. Sorry, watching my time because I know how many slides I have at the same point at this as well. So security is actually a tremendous concern because once IoT devices go out there, in almost every case, they don't have this request-reply device initiation. So they never get updated. This is the camera problem. Somebody has to physically go and update the cameras or tell them to update the camera. Nothing can talk back and forth. It doesn't have that capability. Security is. Traffic considerations. Some of these devices down here are actually fairly simple. Believe it or not, the robotics controls are fairly simple for here. Smart homes, fairly simple. Trucks and trains, not so much. Again, the amount of data that, I can't remember the numbers exactly, but the amount of data that the Google driverless car handles every second and throws away is something like 2 billion bytes. So there's a tremendous amount of data just in driving a car. Now you don't save all of those things. There's a smaller subset that you really want to have. And when we look at those proprietary protocols here, most of the time it's been done in HTTP and REST. But again, they're one direction, so you can't talk back to the car, or you can't talk back to the various pieces here. If you did that, you'd have to have the full capability down on the device, and you get into heavy weight, and then you get into power constraint problems and all those various pieces here. MQTT was designed to solve this specific problem. Bidirectional, support the various pieces here, offer all the various things, and expand it to have quality of service environments. And by the way, JMS does play a role here. JMS fits on top of MQTT the same way that it fits on top of AMQP. And if I haven't overwhelmed you with acronyms, wait, I've still got a few slides to go here for this. So those are the things. And what we're seeing is MQTT is becoming the standard of choice. And that's because there is an upward compatibility element in that standard, and because it is completely an open standard. For instance, if you don't like my company's solution, go someplace else. Don't rewrite your apps, just get a new message router for that. The edge has got a different set of problems. I've answered this a little bit. How many connections do you have here? Are those connections always on, or do they have to rejoin? Let's use our car piece here. The car goes through a tunnel. Does it keep connectivity or not? When it rejoins, where it rejoins becomes important, and what data was either passed or not passed is equally important inside of here. Burstiness. Using Singapore. 200,000 cars here. At rush hour traffic, there can be 80,000 cars on the road in Singapore. At 10 in the morning, it might be 20,000 cars. So there's a burstiness aspect to here. Passing 4 messages per second per car means that your burstiness rates can go up and down pretty significantly here. And you've got to be able to absorb that. Congestion, everything's coming into once. What if you have what's called a slow consumer? Somebody up here at the top who can't take data that fast. So you got to have buffering capability inside of here. Is it multi-protocol? I would pretty much be willing to state these guys up here don't use MQTT, because MQTT is really designed for this aspect down here. So how do you get from here to here? Usually it goes from MQTT to JMS or MQTT to AMQP inside of here. QoS and security. Security, security, security. But in fact, the next generation of both AMQP and MQTT are focused on security. There's other things creeping into it, but right now, the MQTT working group meetings Wednesday mornings, you can go join, just looked on the OASIS site, all about security. That's all we're talking about. Similarly, the edge used to be REST, same problem. It's now moving to MQTT. And similarly, we don't see as much JMS in the edge. We do see some. When we move to the core, scale is not much of a problem. We have big data servers. We have all these various pieces inside of here. But it needs to be enterprise capable. It needs to actually be able to handle transactions. It needs to actually be able to handle those once and only once. So think of it this way, you go off to iTunes and you buy a new song, you really only want to be charged once. You don't want to be charged because 6 message queues saw the message and all processed it for you. You want once and only once for that. So that becomes the thing here. And with the new world of containers, microservices do come into play, and our scale is beginning to creep up. These messages can get passed around a lot of different places here. Here, we're seeing REST, of course. We're seeing AMQP 1.0 coming into play. It's been slow. like everything else in standards-wise. It was finalized in 2014. There were earlier versions of AMQP. There's a 0.8, there's a 0.9, there's a 0.91. They are not upwardly compatible. After 1.0, we have a guarantee that we will make all those pieces upwardly compatible. But prior to 1.0, it does require a rewrite to go from 0.9 or 0.91 to 1.0. JMS plays because JMS sits right on top of Cupid, and therefore AMQP just does things. It's really all about the data, very honestly. When you come into IoT, that's the level of data you're talking about, very honestly. It's drinking from a fire hose right here. And to do that, you need to be able to set up some sort of level of buffering capability inside of here. The buffering capability is because you don't know how fast or how much data is going to come in at any given moment for here, and you have some limitations over here. How fast can you consume it? What happens if something goes down? The consumer stops working. Now it can't consume anything at all. And what's actually happening to your bandwidth at the same point in time? You know, in my fairly small 8-person office, I get there bright and early and I have great bandwidth, wireless great bandwidth. At 2 in the afternoon, my bandwidth sucks big time, very honestly. Stanford University, you'd think it has great bandwidth. It does, about 10 at night, okay? In the middle of the day, when there are 7,000 students sitting there and 10,000 staff and 8,000 professors, there's no bandwidth. I actually carry my own little portable Karma because my bandwidth on my Karma is faster than anything else. So scalability here, again, how do we talk from here to here? I said we'd talk a little bit about this. Sending a message to a specific device, or the device is sending it and expecting a reply from those 2 devices here. You have millions of devices, you're going across 2 middleware tiers here, and how do you connect these things? So he talks in, he talks to a different piece, he wants to talk to that guy, he talks to here, this talks to here, this talks to here. The only way to resolve this issue right now, when you know this is going to have to happen, is setting up persistent queues or topics. Queues on this side, topics on this side, so that he knows to push it to a specific queue, publish subscribe model, and he knows to push it to a specific topic. All those wonderful little computer IDs and so forth are useful if you have lots of devices that are connected to a queue. You can have this guy down here say, I'm only subscribing to things with my serial number, so anything else I'm going to ignore. And in fact, your message bus won't even deliver it to him, but that's where that falls into place here. MQTT topics are your friends, and when you talk about this. And the queues on the top end, the AMQP, JMS queues at the top end are the way that you have to tie together. If you have messaging, you already have queues. I will guarantee that you have queues. If you have any sort of messaging, you have a queue. What you need to do is tie the queue to the topic. And the topic has to be persistent because the queue has to know where to find the topic. We're trying to solve this. Again, this is not a trivial problem to solve here. And the biggest headache is if you set up persistent queuing, how do you handle that burstiness problem? So all of a sudden, I have not one thing I want to talk to, I have 10 million things I want to talk to. I can't talk through one queue. No queue is going to be able to handle that in a timely fashion. So it's Singapore land thing. Every car in Singapore, if you drive in Singapore, you will have this thing called an OBU, on-board unit. It's about that big, and every car is required to have that for you. By the way, you may think of it as expensive, but the Ford Mustang, brand new 2015 Ford Mustang, is $200,000 US in Singapore, just to give you an idea of range for that. It has roughly 200,000 cars on the road right now. Those cars are MQTT terminated, and they have to respond to request reply. So when there's an update, they sends it off to the car and says, hey, here's my message, you turned yourself on, asked for an update, here's your update for that. It also has absolutely persistent messaging. You don't want the car to not report something that's important, very honestly. You want it to stay there. Even if it goes through a tunnel, it stores it locally, caches it, and delivers it in order. because you need to know if somebody hit the tunnel, realized they were no longer on the grid, and decided to do 150 miles an hour through the tunnel. By the way, nice thing about Singapore, there are no parking meters. Park your car. Just park your car. Your car knows it's parked. It will charge you however many minutes. So you don't pay for an hour, you don't pay for 2 hours. You pay for the exact amount of time. The downside, you park illegally, you will get a ticket for this. They have not gotten to the point where they are giving you tickets for speeding based on this report, but it's probably coming for here. So over here, whoops, wrong button again. Over here, there are 3 things that are currently done now. Routing server, this road's too busy. Your car comes on and says, hey, if you go this way, I'll charge you less, because every road has a fee associated with driving on in Singapore. That's the payment aspect here. And then it says, oh, look how many cars are going on. Look how many of these are going on here. And then down here are all sorts of things. So our architect, who's in Singapore and works on here and lives in Singapore, points out, for instance, that the section outside of his house, which is never really busy, he tends to exceed the speed limit a little bit. And he gets letters from the local authorities saying, no, don't do that again. Imagine what would happen if his insurance company had that data. And it's a piece of cake to write the analytics. Fortunately, privacy law doesn't let that cross over yet. But there are all sorts of things that you could have down here that just haven't been thought of at this point in time. Bus monitoring. There's this thing called bus bunching. Google it at some point in time. But basically, it's a bus comes along, you're waiting for the 14 bus, no bus, no bus, no bus, no bus. Well, every single thing inside of Singapore, for instance, has a sign that says when the next bus is coming. You can look at it on your phone. It says when the next bus is coming, to what stop, how far away they are, and when they should arrive there. And bus bunching is, the 14 bus doesn't show up for 45 minutes. And 14 bus shows up, and behind the 14 bus are 4 more 14 buses for here. Now, with these analytics, they can actually send messages to drivers and say, you need to take a different route because this guy's stuck in traffic. There's been an accident. There's something going on here. And they can spread the buses out. It's a similar problem with taxi cabs that fall into place here. And it all goes up so they actually can look at this from a dashboard viewpoint and know what the regulations look like here. So, summing up here, IoT connectivity, this is an architectural problem. It's not simply as cool as saying, here's some really cool devices, go forth and do something inside of here. Yeah, you can do it with a single bus approach, but what we're seeing as in real world examples is this double bus approach. The bus actually works much better. It solves the whole problem of looking at a unified address space inside of here. And very honestly, you need to know what your quality of service requirements are and make use of them. And honestly, you need to support all of those types of message exchange patterns. The first 2 and the second 2 kind of group together. So if you get the first one, you're probably going to get the second one. If you get the third one, you'll probably get the fourth one. But what you now really need is 1 and 4. So you really need to be able to have all 4 of those. At the edge, it's all about scalability, connections, and how you set up your subscriptions. REST, MQTT, CoAP only if you are in a subnet or willing to put up with some interesting bridging things here. And security is something you have to worry about and is a very finicky problem at this point in time. We're working on it here. At the core, single point of contact point for here, APIs that manage from a cloud, enterprise data center database back out to here, message filtering because that device doesn't want to see 400,000 messages coming from cars every second for that, and be able to scale horizontally. As you add more cars, you need to be able to add more capabilities to be able to do that. And finally, because this is a lot of data, integration with Hadoop is pretty darn important. It is sort of the model sense. So, summing up, I can't tell you what IoT is going to become. I can tell you it's here, for here. And once you built it, changing it is not cheap. If you've ever heard, those phrases, this is a new one. If it ain't broken, don't fix it. If you touch it, you will break it. Fixing it is expensive. This is my 4th one. Changing your infrastructure is going to make fixing it cheap for that. So you need to be able to make flexible data movement. You need to be able to move things in and out as you need them. Not being dependent on any single vendor to provide support, not being limited to a single product set. Go with standards. And once you're with standards, you have the power to pick and choose what works best for you. So decouple the concerns, make sure you use the right standards. Because I'm an open source geek, I like things that have open source connections and roots to them. So using the open source product APIs makes sense to me. And finally, keep in mind you're always doing this for the user, no matter what. And that's it. We have a free copy of the virtual message router, which runs in almost anything, Pivotal, AWS, on your laptop, whatever. Feel free to go grab it, deb.solace.com. It also connects to our open source laboratories, so we have a number of open source projects out there as well as a whole series of classes. If you didn't catch all my acronyms, they're out there as well. Thanks, and then got a few minutes, I think. Questions? I have 5 minutes. Wow. If not, thanks for coming in and listening to me. Yes?
What about the device management? We talked a lot about data coming in and out and all that, but how about the relationships of the device, like for an organization, for example, right? Like the Singapore city, they probably want to know what are my buses.
Right.
And like basically provisioning those devices, managing the relationship.
So there's two things. Each, because of the way that it's hidden in here, the MQTT, what's called termination, is the indication specific to an MQTT device. So it is part of the message header that says what the device is and so forth. There are a handful of applications, and SAP HANA, for instance, has them built in that will terminate MQTT and manage the device sets for you just by connecting them in and saying, go talk to this. It automatically does a subscribe model for you. The subscribe model then fills in that management portfolio, that picture. Other than that, you're pretty much writing it on your own right now. Anything else? If not, thanks for coming. I will be down in the booth until it closes. If you want to stop by, we're downstairs that side for this, if anybody's got any other questions. And again, enjoy the rest of the show. Thanks.